Hello, my name is Maureen Dawn, and I'm a PhD student at the University of Washington. Today, I'm presenting TASM, which is a tile-based storage manager for video analytics. Both due to the increased prevalence of cameras everywhere, along with advances in deep learning and computer vision, users are increasingly analyzing video data. We're seeing more applications that collect and analyze it. And as a result of this increased interest in applications that process videos, there have been a number of recent video data management systems that focus on accelerating queries over videos. The goal of this talk is to think for these systems, what would be a good storage manager that could help them further accelerate their query processing? One challenge of working with stored videos is because they are so large, they have to be stored in a compressed format. And encoding and decoding from this compressed representation are expensive operations. And so our storage manager has to efficiently retrieve data from this encoded representation. So again, the question that motivates this project is how can we store videos in a way that makes them efficiently queryable? Before I talk about what TASM does, I'll first give a little bit of background on how video encoding works. Let's say that a user executes this query to retrieve the dog from the video. And so what the query processor wants to return are just these pixels around the dog. However, it can't directly access those pixels because the video isn't stored as a raw pixel matrix. That would be too expensive. Instead, the pixels are organized into frames, and each frame is encoded. However, we can't jump directly to this frame because there's a second level of compression for groups of frames. So videos are organized into what are called groups of pictures, or GOPs. And each GOP is a sequence of frames that's encoded independently from the rest of the video. And the start of the GOP is a temporal random access point into the video. So for example, to get to this frame with the dog, we don't have to start at the beginning of the video. The decoder can instead start at the beginning of this GOP and decode frames until we get to the one we're interested in. And so with this in mind, of how video encoding works, we can think of the key operations we want our storage manager to have and how we can implement them. So the first key requirement is that we want efficient sequential and random access into the video. And this is actually straightforward to do with the GOPs, because if the user executes a scan that starts in the middle of the video, all we have to do is find the GOP that starts closest to that point and begin decoding frames from there. However, we also want to efficiently be able to read sub-areas of frames. And we want to do this because often the query processor only needs to operate over a subset of the pixels. For example, to blur license plates for privacy, it only needs to modify the parts of the frame that contain cars. Similarly, if we're trying to look at the animals that pass a wildlife web camera to classify them as injured or healthy, again, we only need to look at the parts of the frame that contain the animals. And so to address this need to be able to efficiently access into frames, we introduced TASM, which is a tile-based storage manager that breaks video frames into tiles and optimizes the tile layout to accelerate queries. And so if we think about what tiles actually are, through a recent Codec feature that let us split frames into independently decodable pieces. And so if these white dashed lines represent tile boundaries, now we can decode just the lower left portion of the frame that contains the dog. So in current systems that don't utilize tiles, to execute this query, we had to process 3 entire frames. And all of these pixels in blue were decoded, but not actually used in the query. And so they're wasted work. If instead we encoded this GOP with a tile layout, we can significantly reduce the amount of unnecessary work we have to do by only processing the lower left portion of each frame. A simple example shows the potential of using tiles to reduce the amount of unnecessary work systems do when executing queries. Now let's look more closely at how we can actually use tiles and optimize their layouts. A tile layout describes how each frame is divided into tiles, and the layout specification maps each GOP to the layout it uses. A useful feature of tiles is that each GOP can use a different tile layout. And this is helpful because it enables us to optimize the tile layout at a very fine scale within the video. Because as objects move within the frames and come into frame and leave frames, we can pick a layout that's good for just where the objects are for the few frames that make up the GOP. One restriction of our problem formulation is that we make it so that each GOP can only have one tile layout at a time. For example, we don't keep around one layout around dogs and another around cats. We observe that some tile layouts are better than others, and this depends partially on the queries that users execute. The cost of executing a query over a video encoded with tiles depends on how many pixels are processed, as well as how many tiles are processed, because there's an overhead for each tile we process. For example, this query to retrieve the birds from the video, the layout on the right is better because we process fewer pixels and fewer tiles. Some further challenges to finding good tile layouts are first that objects move over time. And so we can't expect to have great performance if we use the same layout for the entire video. Additionally, objects are discovered as queries are executed, which means we can't pick tile layouts ahead of time because we don't know where objects are at that point. We need to incrementally update the tile layouts as we learn where objects are. And then finally, queries change over time. And different users may query for different objects, or users may query for different objects in different parts of the video. And so we need to be able to adapt and update the layouts as we learn more about the workload. Now let's look at how TASM addresses these challenges and finds efficient tile layouts. Again, TASM is the storage layer that interacts with the query processor. Initially, nothing is known about the video, and so when we get the first query for dogs in the first minute, the query processor gets the first minute of video from TASM, finds the dogs using an object detector or specialized model, maybe it does some further processing, and then it returns them to the user. At this point, the query processor adds those detections to TASM's object location index. TASM uses this index to later on design tile layouts around where the objects are in frames. TASM also keeps track of the queries we've seen so far as possibly useful layouts to eventually create. So this process continues. Let's say the next query is for cats. In the first minute, again, the query processor finds the cats, maybe does some further processing, and then returns them to the user. It adds those detections to the object location index, and TASM updates its set of possible layouts to be all possible combinations of queries we've seen so far. And this continues as queries come in, but eventually TASM needs to decide if it's going to retile GOPs, and if so, what layouts is it going to use? So the question is, how can we automatically do this? And again, what we want to do is automatically tune the tile layouts of these GOPs over time. To do this, TASM uses a regret-based tuning technique, where regret measures the difference in cost of executing the query over the current tile layout compared to some alternative layout. Initially, each GOP is untiled, and all of these alternatives come from the queries we've observed so far. We estimate the cost using a cost function where the cost is proportional to the number of decoded pixels and tiles. TASM retiles a GOP when the accumulated regret is larger than the estimated retiling cost. Again, the regret measures how much time we would save if the GOP had a different layout, and the retiling cost is the estimated time to re-encode that GOP with a different tile layout. So as queries come in, TASM updates its regret for each combination of GOP and alternate layout. Let's say at this point, the layout around dogs for GOP1 accumulates enough regret to be larger than what we think the re-encoding cost is. And so at this point, TASM retiles GOP1 with this new tile layout, and it leaves the rest of the GOPs unmodified until their regrets also become large enough. If we look at how this performs, in this experiment, we measure the speed up of an end-to-end application where queries request encoded video fragments with boxes drawn around the query object. For example, this image shows a single frame with boxes drawn around cars. For each query, we detect objects if they haven't been detected yet, and then we remember where they are so that future queries only need to add the bounding boxes. The place where TASM comes in is that to draw the boxes, we only have to modify the parts of the frame that contain the objects. And even though TASM only accelerates the storage access part of the query, we still see significant improvements compared to operating over an untiled video. The paper has all of the details for this experimental setup, as well as many more experiments. So in conclusion, today I presented TASM, which is a tile-based storage manager for video data. It breaks videos into tiles and optimizes the tile layout to accelerate queries. And we've shown that TASM accelerates queries over time. A further benefit that I didn't talk about today, but is in the paper, is that TASM can also speed up initial object detection queries by using an initial tiling based on regions of interest, for example, foreground regions, rather than high quality object detections. Thanks.